consultation in finance, sabermetrics, medical, education. And when I was going through his web page, I mean, he has done, he's a prolific researcher, has, written, you have to really go through, give you time to really go through all his publications. But most interestingly, as an application of mathematics, he has even published papers in marketing research, in communications, in auditing, and he has written books in very interesting topics. And of course, he is a prolific teacher also. He has guided many students for postdoc, for PhD, for even summer interns. And we are very happy to have Professor Stephen Miller with us. And his title of the talk is also very interesting. It's Connections of Class Numbers to the Group Structures of Generalized Pythagorean Triples. Professor Stephen Miller.
Thank you so much for the invitation. Before I begin, I have just two quick questions. I am recovering from a bad cold. Are people able to hear me?
Yes, sir, we can hear you.
Okay, excellent. And then are you able to see my slides?
Yeah, not yet here, but maybe just a few seconds.
Can you see the slides now?
I'll let you know once it comes here.
It said it was sharing on my screen, so let me try again. Do you see them now?
It's still, the slides haven't come yet.
All right, so on my system, it says it's sharing. And so I will try one more time. And then if this doesn't work, I will go to the backup plan.
Yeah, it's coming. Yeah.
Do you see it now?
Yeah, sure. Now we can see.
Okay.
Yeah.
When
please.
in doubt, always reboot the system. Okay.
Yes, sure.
So thank you so much for the invitation. I think I've turned off the video because I am doing this from home and our internet is not often the greatest. This is actually my third time giving a presentation at an Indian conference. Unfortunately, not in person this time, but hopefully that can be remedied next time. The previous two times were with colleagues doing random matrix theory. And one of the reasons I've been able to work in so many diverse fields is that I've had the fortune of working with so many great colleagues. And in fact, at the end of this talk, I want to talk a little bit about a program that I helped create with a couple of colleagues in response to the pandemic. And in fact, if it wasn't for that, I wouldn't have met a lot of the students who this work is joint with. And in fact, they are the ones who did the really detailed calculations here. One of them, in fact, is studying in your country right now. And to me, this is one of the few positives of what we've been going through as a world for the past year or two, is that it's really helped us break down more barriers and talk to more people and work with people we wouldn't have otherwise, go to conferences we might not have gone to otherwise. And so what I want to do today is talk a little bit about some connections of class numbers to some standard problems in Diophantine analysis. Some of the results are hopefully old to a lot of people in the audience who can help me and give me some really good references for these and related problems, and really looking forward to the insights you will have on these. I do a lot of work with undergraduates. My school has no graduate program, and so I'm always looking for interesting problems that are accessible to a wide variety of students with very different backgrounds, that have many different avenues for entrance and many different possibilities to delve into. And so what I loved about this problem is this came from a paper I had read in the past year, is that it was very accessible, but quickly led to some interesting questions related to class groups. All right, so let me just briefly set the stage. So the goal for the talk today is threefold. I want to review the parameterization and group structure of some famous solutions to Diophantine equations. And I want to talk about how we can generalize some of these results from systems that we are quite familiar with to new systems, and see in particular how it's going to depend not just on the class number, but also on the structure of the class group. And then if time permits at the end, I want to talk a little bit about this program I helped create that I mentioned, the Polymath Junior Research Experience for Undergraduates. We are always looking for professors, postdocs, graduate students who would be interested in helping us guide students in research. And so if anybody is interested in doing that, I hope you will reach out to me either after the talk or later. My slides are online on my homepage, as is all my contact information. Okay, so what is the general framework? So if you have a Dirichlet equation, so that's going to be a polynomial, a system of polynomials with integer coefficients, and you're looking for rational solutions. The natural questions are first, are there any solutions? And then if there are solutions, are there finitely many or infinitely many? And then if there are infinitely many, can we generate them? Is there a structure on the set of solutions? So these problems have been studied for millennia. So one of the oldest is the Pythagorean triples. So this is one of the mandatory slides that you have to include in talks like this. The only flexibility you have is what you want to declare as your special point. Do you want it to be -1, 0? Do you want it to be 0, -1? It's essentially the only freedom you have in giving a talk like this. So I chose to take the point -1, 0. And what you can show is if you're looking for solutions, a squared plus b squared equals c squared in the integers, well, if we divide through by c squared, that's the same as looking for rational solutions, x squared plus y squared equals 1. And so if I have a point on the unit circle with coordinates x, y, and I draw the line from -1, 0 to it, well, we see that if x, y is rational, the slope is going to be rational. And conversely, if I start off at -1, 0 and draw a line with rational slope, it's going to intersect the circle at a rational pair. And so there's a nice one-to-one correspondence, and this gives us a beautiful parameterization of the rational points on the circle in terms of these slopes. And explicitly, it leads to being able to write the triple for some co-prime integers n and m as m squared minus n squared, 2mn, m squared plus n squared. All right, well, instead of looking at the Pythagorean triples on the unit circle, another item we can look at is elliptic curves. One of the nice pleasures of being a postdoc at Brown is you have access to Joe Silverman's text code, and you might recognize these images for his book. And so, an elliptic curve of the form, y squared is x cubed plus ax plus b, we're looking for rational solutions. And because the degrees work out just so right, if I take 2 points p and q as rational coordinates and I draw a line through it, well, that line's going to have rational slope. It's going to intersect the curve at some point r, and then the reflection of that point is how we will define p plus q, and that will also have rational coordinates. And it turns out that there is a group structure on the set of rational points, and it's equal to some torsion group plus some number of copies of z. And so Mazur proved that there really aren't that many possibilities for the torsion group. It's basically a cyclic group or the cross of some cyclic groups. And this, of course, can be generalized to number fields, not just for the rationals. The rank is far more interesting and would be worth 3 or 4 talks just by itself. Below is a little plot of the known elliptic curve rank records as a function of year. And there are some beautiful, beautiful current conjectures that say the rank might not actually be unbounded, but there might only be finitely many curves of rank beyond, say, 28 or something like that. So a lot of work is being done on this right now, but the point to get from the Pythagorean triples and the elliptic curves is that we have ways of parameterizing points, and we have ways of taking solutions, taking points in the group and constructing new solutions. And so I recently read a paper by Amnon Nicotilli about trying to do this a little bit more explicitly, some of the insights from elliptic curves on Pythagorean triples. And so there's a link in the slides to his paper. And basically what he did is the following. So let G of Q be the set of points A plus BI with rational coordinates, such that A squared plus B squared equals 1. So a point on the unit circle. So P sub K is going to denote the primes that are congruent to K mod 4. And so, well-known classical result, going back only a couple of hundred years, not a couple thousand years this time, is that if your prime is congruent to 1 mod 4, then you can write it as the sum of 2 squares. And you can immediately, of course, see why this would be a useful result when we are trying to study writing points on the circle. So we take our solution and we normalize it so it's now on the unit circle. So we take m plus ni and we divide by m minus ni. And he showed that the abelian group decomposes into a product of the units and a free abelian group where the basis is going to be just a collection of these points, zeta of p as p ranges over the primes that are congruent to 1 mod 4. And then when we're counting, we always have to just be a little bit careful as to exactly what do we want to count. If I give you the point 3, 4, 5 as a Pythagorean triple, well, of course, there's also the point 4, 3, 5, negative 3, 4, 5. And so we want to just choose a normalization. And so as long as we don't have a unit, if we have a point, a over c plus ib over c, there are, 8 conjugate points. And so, plus or minus zeta, plus or minus I times zeta, and then the same things with the complex conjugates of zeta. And so you can always adjust and say, well, let's just look at the one in the shaded octant in the image. In the Dirichlet equation we're going to study in just a little bit, we don't have quite as much symmetry as the unit circle, and we won't be able to specialize to just being in this octant. It'll actually just be in the upper right quadrant. But it's the same idea. So we are not going to be counting all solutions. We're going to be counting all solutions up to these trivial conjugations. And just if you haven't seen this before, it's a beautiful way to construct non-trivial Pythagorean triples from known Pythagorean triples. So if we just write our points as complex numbers, we can then use the properties of complex multiplication to generate new solutions. So one possibility, of course, is to just keep taking powers of a point. So if our point is 3/5 plus 4/5 I, if we then square it, cube it, take the 4th power, as the table shows, we go from the triple 3, 4, 5 to 7, 24, 25, and so on. Or if we take 2 triples, 3, 4, 5, and 5, 12, 13, we have a way of combining them and getting a new triple by just writing them as complex numbers, multiplying them, and then from that just going to our triple. And of course, here I've written it in a normalization. All right, so let me just go through some preliminaries, and then I will state our main result, and then I will give a quick sketch of the proof as time permits, as well as my voice. I am hoping that I can get through this talk, and I appreciate your patience trying to listen to me as I fully recover. So we're going to be looking at the Dirichlet equation x squared plus dy squared equals d squared for various choices of d. And so similar to the Pythagorean triples, we'll define gd of q to be numbers of the form a plus b squared root of negative b, which solve a squared plus bb squared equals 1, and a and b are going to be rational numbers. So very similar to what we did before, if we have a solution, x squared plus dy squared equals z squared, we can normalize, we can divide by z, and we can choose it to be in the upper right quadrant if we wish. And so this turns out to be an abelian group under complex multiplication. A good way to see this is to look at the norm. The norm is multiplicative. So if we have a solution, we can, very similar to what we did before, combine it and get a new one. This should not be too surprising, of course, because what we did before in the Pythagorean case is just the special case d equals 1. Because we now have the more general d, we can't, of course, just interchange x and y, and that's why we lose a little bit of the symmetry, and we're going to only have 4 conjugates rather than 8. And so the main theorem that my students were able to prove, and this really is their work, my job as the mentor was break glass in case of emergency. It was wonderful. They hadn't really seen much of the subjects before and did a phenomenal job devouring the literature, reading the paper, mastering some elementary results about class numbers, and then trying to figure out what they needed to do to solve this problem, and what conditions do they need to do, and what d's could they attack. And so what they were able to show is that if d is congruent to 1 or 2 mod 4, and suppose the class group is a free V2 module, then we have a result very similar to what Yekatiel had before, where we have it as the group is going to be written as the form units cross F, where F is a free abelian group. And we'll talk a little bit later about, how we generate it. It's going to be, very similar to what we did before. And we even have, a formula which tells us, how many solutions do we have for a given value of C, which is going to be a function of its prime factorization. And this is, generalizing again the result of, if I want to know how many Pythagorean triples do we have, the form a squared plus b squared equals c squared for a given value of C. So just to make sure we're all on the same page, especially since I think there's two different ways of defining binary or quadratic forms. So I'm going to use ax squared plus bxy plus cy squared, and the discriminant is going to be defined to be b squared minus 4ac. We'll say quadratic form properly represents a number if there exists relatively prime integers x0 and y0, such that the form at that point is equal to m. We'll say the form is primitive if no number divides a, b, and c, so the GCD of a, b, c is 1. It's positive definite if d is less than 0 and h greater than 0. And the one that we're going to be interested in most, not surprisingly, is when the discriminant is negative 4d and our form is 1x squared plus 0xy plus dy squared, because we're trying to study, my apologies, we're trying to study when can we write, or what can we say about the solutions of x squared plus dy squared equals z squared. And so I'm not going to go through this in too much detail, but just a lot of the talk is just recalling standard results about binary quadratic forms and the associated groups, and some results about their solutions. So the slides have the full details if anybody's interested. I am happy to chat a little bit more afterwards. So the number is just a bit standard that helps us talk about how we can combine two binary quadratic forms and create a new form from that. And so this is going to be the famous Dirichlet composition law. And so the lemma just basically says how we can get from capital B, which we then use when we combine. And so the new form capital F of xy is going to be a prime x squared plus bxy plus b squared minus c over 4a prime y squared. And so we'll denote this Dirichlet composition of f and g by f star g. And it's going to be important to note that we have many ways of acting on the forms. The set of 2 by 2 matrices with integer entries in determinant 1, the special linear group, acts on the set of quadratic forms as follows. We just replace xy with px plus qy and rx plus sy. All right, so what we're going to do is we're going to be looking at the class group, and we're going to see how the class group affects our ability to describe the number and the structure of the solutions of x squared plus dy squared equals z squared. So the orbits of SL2z on the set of primitive positive definite forms with discriminant negative 4d forms an abelian group. We'll call this the class group, and we'll denote it C of negative 4d. And the operation on this group is just the Dirichlet composition we talked about. And then, there are some standard remarks that this is related to the ideal class group, which is related to fractional ideals. So just as a quick consistency check to make sure, if we say it's a group, then there should be an identity element. And fortunately, the identity element, which we'll denote by E of xy, is just x squared plus dy squared, which is precisely the form we want to study. And of course, this is not a coincidence. So to see that this truly is the identity, we just have to look at the Dirichlet convolution of this form, E of xy, with any other form, f of xy, and then just standard calculation of using the lemma we had a few moments ago shows that everything works out, and we do get back the form f of xy. So what I want to do is, especially since it's about 1:30 a.m. for me, is rather than trying to go through all the technical details, I want to give instead a high-level overview of what's going on. Explain the key ideas, explain why we have the conditions we do in our theorem, and try to just give you a general sense of the proof. And then we hope to have the paper finished in the near future. This was a collaboration spanning a couple of weeks in the summer as well as several continents. And so unlike a standard program where we get to be in person working together, this was complicated by multiple time zones and different schedules. But we are close to having things finally written up at this point. All right. So our aim is to factorize each element and find a normalized solution, and then we'll count how many normalized solutions there are. One of the problems is that the structure of z square root of negative d can be far more complicated for general d than when d equals 1. We don't have the same beauty we have with the Gaussian integers. But as long as it's a free Z2 module, you'll see that everything is okay, and we can still mimic the calculations without too much detail, without too much trouble. This doesn't mean that the results only hold when it's a free Z2 module. And in fact, at the end of this talk, we'll give some examples of some other choices of D where the class group is not a free Z2 module, but we have similar results. And then we'll also give a few examples where it is not a free Z2 module and the results do not hold. So, this simplifies a lot of the analysis. This allows us to prove it in many cases, but we're not saying these results only hold for such D. All right, so what's going on? So, the class represented by x squared plus dy squared is the identity element in the class group. And so we want to solve x squared plus dy squared equals z squared. And so we're looking for which numbers, z squared can be represented by the identity form, the x squared plus dy squared. And so, standard calculation is if, the form f represents n1 and g represents n2, then the Dirichlet convolution represents the product n1 and n2. And so because we have the form we care about, the x squared plus dy squared is the identity, and we're assuming the class group is a free Z2 module, every element has order at most 2. It's either the identity element and has order 1, or it has order 2. Well, if it has order 2, that means, f Dirichlet convolved with itself is the identity element. That's the form we want. So if we want to try to represent, say, some number c as x squared plus dy squared, if we can represent, if we want to represent c squared as x squared plus dy squared. Well, if there's some form that represents c, so if f of xy equals c, then f star f represents c squared. But f star f is the form we care about. It's just the x squared plus dy squared. And this is the advantage of looking at the very special case when the class group has every element of order 2. So this is a little bit more general. Initially we were looking at, the class number was 1 or the class number was 2. We actually don't need to be quite that restrictive. We just need every element to have order 1 or 2. And so, this slide is basically just repeating what I just said, is that if some form represents C, then f star f represents C squared, and f star f is the form we care about, the 1, 0, d, the x squared plus dy squared. And so our method of proof breaks down if we don't have a free Z2 module. Again, that doesn't mean the result fails. It just means that this line of attack is not going to be able to prove it. Okay, so again, we could try to prove the normalized solution, trying to find a primitive form that represents C. So given some C, can we find some form that represents it? So we're going to do an analysis, a local analysis, look at what's going on for each prime, and look at the decomposition of some number C as a product of primes, and try to build something up from that. And so, just briefly, to get some intuition, looking at what Dirichlet did, he determined the group structure. He represented the Pythagorean triples as complex numbers on the unit circle. He looked at the primes that were congruent to 1 mod 4, which could be written as sums of 2 squares. And from that, he got the complex numbers, zeta p, that have modulus 1 and are under the unit circle. And that's the concept that we're going to be generalizing as we go forward. Which of these primes leads to nice numbers like this? And again, his main result was that the group of rational solutions can be written as units cross F, where F is a free abelian group with basis of these zeta p's. And further, he was able to count how many normalized solutions we have and got to the k minus 1. And so if C is of this form, where it can be written as a product of primes that are 1 mod 4, then the number of normalized solutions is 2 to the k minus 1, and otherwise there are no normalized Pythagorean triples. And our result is quite similar. And so again, we're going to assume that D is congruent to 1 or 2 mod 4, and that the class group is a free Z2 module. And then again, we'll have C is the product of our primes. And if negative dpi is 1 for all I, so this is the Legendre symbol, then the number of normalized solutions, again, is of the form 2 to the k minus 1. Otherwise, there are no normalized solutions to x squared plus dy squared equals z squared. And then just trying to give a quick sketch of the proof before delving into some of the details. An odd prime p is properly represented by a primitive form with a discriminant minus 4d, if and only if minus 4d on p, which of course 4 is a square, is the same as minus d on p equals 1. And then a composite number is properly represented by a quadratic form, if and only if all of its prime factors are properly represented by a quadratic form. So again, the idea is to look at analysis locally at each prime and then build it together. And again, crucially, everything that goes on, again and again and again, our argument comes down to the fact that we are using that no matter what form we take, f star f is our identity element, x squared plus dy squared. So if we want c squared to be represented by the x squared plus dy squared, all we have to do is find some form f that represents c, and then f star f will represent c squared. All right, so similar to before, we define for some time zeta of q, x naught plus y naught squared root of negative d over q. And it's a little bit different than the Pythagorean triples, because now we can't just flip the x and the y, because the y is rated by the square root of negative d. That's fine, it just changes the number of solutions. It's not going to change the number of normalized solutions. We then factor elements of GD, Q as a product of the zetas. And then this is equivalent to a factorization of the C. And this equivalence is just going to determine the number of solutions. Okay, so I believe I still have a little bit of time left. If I start getting close to how much time is allotted, please just let me know. And so I want to just put in a little bit more detail of how the students were able to prove all of this. And so S is going to denote the odd prime such that negative d on p is equal to 1. And so we'll assume negative d is 2 or 3 mod 4. Assume the class group is free Z2 module. Assume C has the prime factorization as before. And there exists a normalized solution if and only if negative d on pi is equal to 1 for all of the primes. And so the proof is pretty standard. We take a positive integer, we see when is it represented by a primitive form. So we talked about this. If and only if negative d on p is 1 for all the prime factors p of c. And then as we've said, time and time again, if we're trying to represent c squared, then that's the same as can some form represent c. And this is because we have a free Z2 module, so any form convolved with itself is just the identity, the form x squared plus dy squared that we care about. This is one of the things I hate about doing things by Zoom, rather than being there and being able to just put something on the blackboard and have it there for everyone to see constantly throughout the talk. All right, so by now we've seen this slide so many times, this should be an old friend. For every q in our set of primes, we define zeta of q as before, and then we have the existence of such a zeta of q because of proposition 1.1. And so now we just let z be a plus b squared of negative g over c, and we have c written as the product of the primes, and then z is going to just be plus or minus the product of the zetas, the nearest powers. And again, everything is well defined. This leads to our normalized solutions. And so we just repeatedly use the following lemma to complete the proof of theorem 1.1. So for some time p such that negative b on p is 1, let's let x naught squared plus by naught squared be p to the 2 alpha, where x naught and y naught are relatively prime. We'll assume p to the 2 alpha divides c squared plus d squared for some c and d that are relatively prime. Then exactly one of the following two is true. Either x naught plus y naught squared of negative d, or x naught minus y naught squared of negative d divides c plus d squared of negative d in z squared of negative d. And so, the proof of theorem 1.1 is going to use proposition 1.1 repeatedly. And then, right. So, theorem 1.2, we have our z, we write z as our product. And then if z corresponds to a normalized triple, then c is of this form. And the proof of this is fairly straightforward algebra. Again, we write b1 as a1 plus b1 squared of negative d over c1. Similarly for z2, and then again we can just combine them and get a normalized solution. This is following from straightforward algebraic calculations. This is using a lot of the nice structure of complex numbers. And so for each prime, we just represent it. We have our zetas, and then we combine them. And they just correspond to solutions. And so I either apologize for not going into all the algebraic details carefully or slowly, or hope you appreciate the fact that I'm not going through all the algebraic details carefully and slowly. I'm just trying to give the high level calculation of what we're doing. And so similar to all the stuff that's going on before, if the primes are the right form, then we can find solutions for each one, and we can build them up to a global solution for the given c. And if not, if there's an obstruction, then there is no solution. And so we just have our two different sets. We've established an equivalence between the two different sets, and then we just go through and we look at the number of normalized solutions. And the last remark is just that we have to be a little bit careful because given a solution, we have several different possibilities. We can take complex conjugates, we can multiply by the units, and so this is why we're just counting right now how many normalized solutions are there and not just how many solutions. I think to just end before I talk a little bit about the structure of the polymath program, just where do our results apply? Well, we need the class group to be a free Z2 module. So if the class number is 1, then that's clearly going to work because everything's going to have order 1. So in that case, we look at the famous class number 1 problem, but we want D to be 1 or 2 mod 4. And so if we want D to be 1 or 2 mod 4, the only choices that are going to work with class number 1 will be D equals 1 or 2, because the other ones won't have the right congruence. We can look at the class 2 number problem, and again, look and see which ones will it be when D is 1 or 2 mod 4. And I believe if we've looked things up correctly, the only ones that will work is when D is 5, 6, 10, 13, 22, 37, or 58. The more exciting possibility now is to look for situations where the class number is greater than 2. And when it's greater than 2, we still want to have a situation where each element has order at most 2. So one example is if D equals 210, the class number in this case is 8, but each element has order less than or equal to 2. Some situations where the results do not hold that show that if you remove these conditions, you could have different behavior. If you take D equals 26, the class number is 6, and you would have some issues with some forms properly being represented, but this form has order 3, and we don't have any normalized solutions to x squared plus 26y squared is 7 squared. And then, the results may not hold even if the class numbers are performed true to the n. So, we had 8, which was the last slide, which was 2 cubed. And so here's an example where the class number is 4, but not every element has order 4, so things break down. So for my last few minutes, I want to just briefly talk about the summer program which led to this, and invite people who are interested, please reach out to me, because we are always looking, as I said, for more professors, postdocs, graduate students who are interested in running and helping to run research projects like this. So here's the website to the Polymath Junior program, or the Polymath Junior REU Research Experience for Undergraduates. So it's a collaborative mathematical environment where, to date, most of the professors involved are from America. There's a few from Canada, maybe 1 or 2 other countries. But one of the things that's absolutely wonderful about this program is it's truly worldwide. And so, you can go to the webpage, and here's a snapshot with a little bit more detail. But our goal is to provide an opportunity to any undergraduate who wanted to do research. And this is, of course, an extremely ambitious objective. And if all of a sudden, 40,000 people apply, there is no way we can handle that. The only requirements we really had in the application was that students must have taken at least 1 theoretical class, and students must have a professor who can write a letter of recommendation for support. And for the most part, for the past 2 years, we've accepted anyone who's applied who's met those conditions. We accepted around 300 people last year, around 400 people. I'm sorry, 300 2 years ago in its first year. I think maybe around 400 last year in its second year. We try to have the research groups on the order of 20 to 30 students each. Some students are going to be very active. There were a lot more students who worked on this project than the students I mentioned on the title slide. And we expect something like this because people are going to be busy. Some people will be having jobs that they'll be doing at the same time. Some people will be taking classes. Some people are really interested and want to devote their entire summer to something like this. Other people want to just do this to get a little bit of exposure. We wanted a model that would be somewhat flexible. One of the nice things is because we are doing this all online, we are not paying students. We wish we could pay students, but this relieves us from a lot of pressures that standard research experience for undergraduate programs have in the United States. We are not taking government money for students, so we don't have to worry about visa issues. We don't have to worry about providing housing or stipends. And so we truly can open this up to people from all over the world. We've had a lot of students participate from outside the US, a lot from India this past year. And the only way that this will work and the only way that this can be scalable is if we have more professors, grad students, postdocs who step up and either come to the program with a problem that they are willing to help mentor, or help someone else with one of their problems that they want to mentor. And so for our group, to just give you a little bit of a sense, is I ended up working with several different colleagues. And for some of the projects, we actually had 2 professors working on it. For some, it was a professor and a graduate student. For this one, I was the lead professor in charge. And then Thomas Martinez, who graduated recently from Harvey Mudd, was a former standard REU student of mine. And he assisted me as the research assistant to help run the program. We had 2 high school students, Sydney Morgan and Zayon, who started the project. It began with my giving them a series of lectures on background number theory and having them read the paper, try to summarize it, build some notes. And then I shared those lectures and that work with my college students, listed below. And then the high school students and the college students worked together to try to push these results further. And different students had different amounts of free time for projects like this. And this is probably the greatest drawback of the program, because it's virtual and because people are spread out in so many different time zones, if you don't have the same dynamics of just being in person, being in the room. I was listening to the previous talk and I was just envious of seeing everyone in the audience able to listen to the talk. And then when it's done, well, in a normal time when you wouldn't have to go immediately and listen to me, to just have a few minutes to talk to each other about what you have heard, or what you've been thinking about, just to have those hallway conversations, those conversations over coffee. So a lot harder to have that in the virtual environment, but it is better than nothing, and it does provide a lot of opportunities for students who would not have had the chance otherwise, as well as for the grad students, postdocs, and faculty. It gives you a chance, especially early in your career, to help learn how do you devise a research program, how do you mentor students. It's great practice for a lot of things later in life. So just a few quick open questions and references, and then I will call it a night. So there's many different questions one can ask, and if anybody is interested in pursuing these further, please let me know. I'm hoping to return to these with a new set of students next year, possibly supplemented by some of the students who worked with this year if they are interested in coming back as mentors. So what could we say if the class number is 3? What can we say if we know something else about the structure? What if we knew the structure maybe was every element was of order at most 4? Are there any other conditions we can put on where we might be able to say something interesting? What about other Diophantine equations? Can we find other Diophantine equations that might have something similar? I didn't write this down here, but we're doing, of course, things with binary quadratic forms. We could have, of course, looked at ternary or maybe even quartic, where we have more variables. What can be said in those cases? And what's of course wonderful is we have so many generalizations, and so now maybe instead of the complex numbers, maybe the Hamiltonians come into place, the quaternions. So just for completeness, here's a couple of references. The first is a article that I wrote with some of my colleagues for the notices of the AMS that came out earlier this year. And this is just a subset of all the people who have been working on this. We have, easily in the double digits of professors who were involved in this. And most of the professors were running their own REUs. So this was, only possible because of the very generous efforts by so many people to devote their time to stuff like this. And then the other two are, of course, the more mathematical references. So a really good book for a lot of the results on class numbers is by David Cox, which is available online. And as I mentioned, the paper we're trying to generalize is available on the archive with the link there. So we would like to thank the National Science Foundation. So they provided a grant, which was used by the Polymath program to provide some stipends for graduate students to help out with this, as well as the Journal of Number Theory, which provided some funding to hire some people to also serve as mentors. So if anybody has any questions, I am happy to chat for a little bit as my voice holds out. And once again, thank you for the invitation, and hopefully next time I will be able to attend in person. So thank you.
Thank you so much, Professor Stephen Miller. So let me first see in the in-house participants if there are any questions here. It doesn't seem like here. And so now this is time for the online participants. If there are any participant who has some questions, please raise your hand so that we can unmute you to ask the question.
Sir, I have a question. May I ask?
Yeah, please go ahead.
Sir, recently I have seen a paper where this quadratic forms has been defined, where the action of SL2Z is given on that class of quadratic forms. So can we have a similar questions in that case? Like
so unfortunately, there was a lot of static. I heard about every third word. I heard quartic SL2 actions.
This much I only know. So just by looking your talk, maybe it can possible.
I'm just, can you either repeat the question or could maybe you put it in the chat?
So there is a notion of quartic forms and there is an action of SL2Z on these quartic forms. So can we have a similar question in this case also?
I think that's a great question as to, and I was trying to allude a little bit to this towards the very end in terms of trying to look at, generalizing forms and not just looking at binary. I think absolutely that would be one of the topics that should be discussed and studied next year. And if anybody is interested in talking further about that, I think that would make an excellent, hopefully accessible project for students.
Thank you.
Any further questions from the audience? Yeah, if not, so let's thank Professor Stephen J. Miller for such a nice presentation, and of course for introducing the Polymath Junior program for the young participants here and in other places. It's a very interesting program, and I'm sure some of the students who are here will be interested into looking into. So you can look at Professor Stephen Miller's webpage, and if you have any query, please write to him. Thank you so much, Professor Miller. Thank you so much.
My pleasure, and I hope to hear from some of you, especially some of you students who are interested in opportunities for next year. Have a great day.
Yeah, thank you so much. You too have a great time.